Good morning. It's a Friday or a Monday, depending upon the day you're taking this. And what we've been doing is we've been living in a magical world in physics. You might not think so, but it's been magical in the sense that we've been avoiding the topic of friction. It's kind of an uncomfortable topic, kind of like politics at the Thanksgiving dinner table. But nevertheless, it is going to play a role in what we are going to be talking about. And so we're going to start introducing it today and show you how to do some of these problems, and we're going to have to incorporate this probably from here on out in terms of our things that we're going to be talking about. So why does friction even occur in the first place? Well, the reason why friction occurs is because on the surface of every object that has mass, on the surface of every atom, there are going to be electrons, okay? And these electrons have negative charges, and negative charges don't like being by other negative charges. So at a nanoscale here, what happens is that if I have an object rubbing against the surface of another object, there's little imperfections here in the surface of these objects. Those little imperfections cause these electrostatic repulsions, which are going to oppose motion. Friction can never be generated by itself. You can't have friction. Well, let me be careful of that. Friction will always oppose motion, but if there's an object at rest, friction isn't going to automatically launch an object. But what it is going to do is it's going to prevent forward acceleration. Okay? Now, with this whole concept of friction and electrostatic repulsion, in your personal experience, what resistance is less? Is it tougher to start an object moving or to keep it moving? So just kind of think about that for a second. And what you should realize is that it's always a little bit harder to start an object moving than to keep it moving. That's going to play a role in what we discussed today. So let's get the idea down here. So friction. If I have an object and I try to move it, okay, it's got a weight, and that weight is going to be offset by the normal force. If I apply a force here, that force is going to be offset by the force of friction, and we're going to call that the force of friction right there. We'll call it FF. And what happens is that as this increases, this is going to continue to increase until that is overcome. Okay, and some of your simulations the other day should have shown that you can overcome that idea of friction. Okay, now once I overcome that friction, so this is going to be Newton's first law. Okay, forces are balanced. The sum of my forces ends up equaling 0 up until I overcome that. Once I overcome that force of friction, now my F applied is going to be greater than my force of friction. But this force of friction here is going to be a little bit less than it was up to this point. And that has to deal with the fact that it's harder to get an object started moving than it is to keep moving. We're still going to have a weight, we're still going to have a normal force, but since my applied force exceeds my force of friction, there's going to be a net force. Don't include this in your free body diagram, but just be aware that my net force then is going to equal mass times acceleration. That's Newton's second law. Now, the static friction is what holds an object in place prior to motion. So if I have an object that is at rest, static friction is what holds it in place. If I have an object on a slope and that object doesn't slip, it's because of static friction. It's holding it in place prior to motion. If I push on a desk and it doesn't move at first, it's because static friction is holding it in place. Once an object starts moving, we're going to call that kinetic friction, and that is going to retard forward motion. It's going to impede your full capability of achieving your applied force. Okay, and as we suggested here, static friction, this friction holding in place, is greater than kinetic friction. Okay, so different materials, you may have noticed in your experience during your 18 years on Earth here, have what are called different coefficients of friction. And a coefficient, just like in math, is just a multiplier. And we represent coefficients of friction with the Greek letter mu. It kind of looks like a cursive U here. And we are going to use subscripts to indicate whether it is static friction. Mu s is going to be static friction, the friction for a resting object. And then mu k is going to equal kinetic friction, my coefficient of friction for a moving object. And notice in every single case here, this column is less than this column for the same object. For instance, rubber on dry concrete, in order to get something moving, it has a coefficient of static friction of 1. In order to keep something moving, it's got a coefficient of static friction of 0.8. Notice that wet concrete has a lower coefficient of friction than dry concrete. Makes sense. And all these different ideas here kind of play a role here. Notice Teflon, it's a non-stick coating. It has an extremely low coefficient of friction. That's why it's used in frying pans, because things slide off it. If you look on wax, the difference between wet snow and dry snow, there's a difference here. One thing to kind of point out here in general is that your joints in your body have an exceptionally low coefficient of friction. They glide extremely smoothly. The body is an amazing mechanism, and the physics behind how your joints work is truly a credit to decreasing the amount of friction. If you increase the amount of friction in your joints, then that's going to hurt. Okay? So, mu we said represent the coefficient. So what does that tell us? This is a toolbox equation. My coefficient of static friction is going to equal the maximum amount of static friction, Fs max, that two surfaces can maintain prior to motion, prior to acceleration. That's called Fs max. We're going to divide that by our normal force. And our normal force is how hard two surfaces are pressed against one another. Now, we've kind of started out on an elementary level that that's just the weight of the object. But we're going to find out that we can actually apply forces at angles. We can have forces on slopes. So this normal force is going to be a little bit more complicated as time goes on. But realize that this is going to be the case. And I can then reverse this. I can use a little bit of algebraic juggling and say that, hey, my maximum force of static friction is simply going to be my coefficient of static friction, mu s, times my normal force. Once an object starts moving, then I'm going to use my coefficient of kinetic friction. Bingo. Another toolbox equation. Mu k equals the force of kinetic friction, F sub k, over my normal force. And so we can also rearrange this and say that my Fk equals mu k times Fn. Okay, so let's look at a sample problem here. I'm probably going to have to chew up a little bit more time today having you listen to videos on a normal day. I apologize for that. So let's say you've got a hockey puck. It's sliding with an initial speed of 20 meters per second. They're giving us that. On a frozen, we hope it's a frozen pond. And the puck is going to slide 120 meters before coming to rest. What is the coefficient of kinetic friction? Well, let's lead you down the primrose path here and show you how we're going to solve this. Our givens. Our delta x is 120 meters. Our initial velocity is 20 meters per second. And we know it comes to a stop, so our final velocity is 0 meters per second. That's kind of lurking in the bushes there, that is also a given, the fact that it comes to a rest. What's the unknown? What is mu k? I apologize, I didn't go through the effort of subscripting that k. You'll just have to fight through. So my mu k equals Fk divided by Fn. That was our toolbox equation that we gave you earlier. Were you going to use kinetic friction instead of static friction because the puck was moving? Now, in this case, if we've got a free body diagram of this hockey puck, we've got the weight of this hockey puck, we've got the normal force, and since I'm no longer applying a force with a hockey stick or whatever, the only force acting upon this, that is a net force, is going to be my force of kinetic friction. So that ends up being my net force. So that's something to bear in mind here. Now, since my normal force equals my weight equals mass times gravity due to acceleration. Okay, I may have kind of scrubbed by that a little bit, but basically that is Newton's second law. Your weight is the mass times acceleration. And so therefore, mu k equals Fk divided by mg, which is just a rewriting of that equation right there. Since the puck is decelerating, Newton's second law is going to apply. So that means that my Fk equals F net equals mass times acceleration. And if A equals B, then B equals C. Then A equals C. So I can say that if that's the case, mu k equals ma divided by mg, because ma is the same as my F net. My F net is mass times acceleration. And if that's the case, watch what happens here. A mass divided by a mass, those fall out of the equation, so my coefficient of kinetic friction is simply my acceleration divided by gravity. Now that's all fine and well, but we didn't know what acceleration was. The problem never gave us that. So you've got to incorporate one of your earlier equations here, and they didn't give us a time, so you might as well fall back on the one that you don't need time for, which is Vf squared equals Vi squared plus 2a delta x. Now that's the problem you're going to find throughout the years, that we can't just throw out the tools that we've been using out of the toolbox so far. You're still going to need the hammer, you're still going to need the screwdriver, you're still going to need these tools to work through these problems. You've just added new tools to the toolbox. Now since Vf equals 0, my final velocity equals 0, then 2a delta x equals Vi squared. My acceleration is Vi squared divided by a negative 2x. I'm just kind of doing a little bit of algebraic maneuvering there. And so finally, you get mu k equals my acceleration due to gravity, right there, divided by gravity itself. I'm sorry, my acceleration on the puck, I should say, divided by the acceleration due to gravity. I apologize. And so you crunch the numbers here, and you're going to find out that my mu k of the ice in this situation is 0.17. There are no units with coefficient of friction. They are just simply multipliers, so you don't need to worry about units. It's just a number. Okay. I'm going to pause this tape here because I got to do a second demonstration.